Good evening, everybody. Now, for those of you who don't know me, I'm Professor Deborah Johnston, and I'm the Pro Vice Chancellor Academic Framework here at London South Bank University. And it's my absolute pleasure to welcome you to the inaugural lecture for Professor Yunting. The presentation of an inaugural lecture is an important milestone in the career of a full professor. The inaugural lecture provides an opportunity to do several things: to present the career so far, to introduce their field of expertise to a wider audience, and to update colleagues on current and future plans. And for the schools where the professors are based, it gives a number of opportunities. First and foremost, to celebrate across the staff and student body. Secondly, to strengthen existing relationships, including with alumni. And thirdly, to create new relationships, to reach out to establish new conversations. For the university, for LSBU, an inaugural lecture is a key part of our public events programme because it's our way of showing the wider public the value, the strength of our research and our teaching. So we're delighted to be restarting our inaugural lectures again after the COVID pandemic. We've hosted 3 so far. This is our 4th very special inaugural lecture. And the other 3 are available to watch on our YouTube inaugural lecture channel. And again, we are here meeting in person, and that feels very special. It feels very special indeed. It gives an opportunity for wider conversations, particularly in the reception afterwards. It gives a greater richness of understanding, and it gives a greater gravity, a greater specialness of this milestone. Meeting in person also gives me the chance to rehearse that age-old introduction to face-to-face meetings. You've all missed it, and it's this. Please switch off your mobile phones. Keep in mind we are recording. Toilets are signposted outside, and we have no plans for a fire alarm test, so that if the alarm does sound, please make your way in an orderly fashion to the signposted fire exit. So I know we all missed that. So allow me to introduce Professor Yunting. Professor Gay has more than 20 years of research experience in the areas of refrigeration, energy, hydrogen and built environment, and has a huge range of contributions, projects and publications. He attained his PhD in 1997 from the now renowned Tsinghua University in the Department of Thermal Engineering. And he's been here at LSBU since 2020. He's a chartered engineer, a member of CCiBSE, and a member of the Institute of Refrigeration. So how can I introduce Professor Gay to you appropriately, fully? I could talk about his metrics. I can say that his current H index is 29, and his work has secured in excess of 2,600 citations. He's published more than 64 papers in high-quality, peer-reviewed journals, more than 65 papers in the proceedings of peer-reviewed international conferences, and 2 book chapters. Yunting has been principal investigator and co-investigator on a number of projects funded by EPSRC, Innovate UK, DEFRA and industry sources with significant grant incomes, and his knowledge transfer projects cover a wide range of areas. However, we know that metrics and outputs only tell us part of someone's academic and wider impact. And I think it's important that I introduce Yunting through his wider service roles. He's been Vice President of the International Institute of Refrigeration Commission E1 since 2015. He has represented the UK in international fora. He has been an external examiner for MSc and undergraduate courses for a number of universities. And he is an editorial member of a scientific journal. And of course, since December 2020, he has been appointed as the director of the Centre of Civil and Building Services Engineering. Professor Gay teaches extensively and has shown commitment to providing excellent teaching facilities and to having research-led teaching, to particularly linking students' MSc dissertation projects with industry needs. His commitment to his colleagues and to his students, current and former, was personally shown to me by the number of responses that we received when we sent out messages to colleagues and to former students, and we received a huge range that thanked him for his commitment to their mentorship, to their development. And his commitment through his career can be said to be both long-term and legendary. We had a response from one of Professor Gay's contemporaries who studied at his PhD with him under Professor Yan. And Professor Yan, Professor Gay's PhD supervisor, liked to celebrate his birthday every year with his PhD students and to bring together a range of his students who he would question on research topics while drinking Chinese liquor, I believe. Professor Gay's commitment was that every year he wanted to be among at least the top 3 in terms of drinking ability, but also in terms of answering those questions correctly. So we see a long-term commitment. I thought that there were 2 quotes in particular that really resonated. So, for example, one of Professor Gay's PhD students said, "Yunting is the best supervisor I have ever met. He is inspirational and gives me excellent motivation to help me achieve my goals." And to quote another who simply said this, he said, Professor Gay gave me tremendous support when I started my journey and helped me build up my confidence to conduct my own research. Without him, I would be a different me today. So with these commendations ringing in our ears, please join me in welcoming Professor Gay to deliver his inaugural address.
Thanks, Pro Chancellor, for your introduction. Yeah, thanks a lot. And so thanks, colleagues, for your attending my presentation, and thanks for your time, and thanks for your organization for this. Yeah, it's my pleasure, it's my honor to present my previous research projects, and hopefully I think you can find out some interesting topic from my presentation. And the title of my presentation is Power Generation and Heat Recovery from Industrial Waste Heat and Advanced Thermodynamic Power Cycles, including modeling and experimental investigation. As Pro Chancellor introduced, and my name is Yunting. I'm professor in Building Service Engineering in Build and Environment Architecture the school. And also, I'm the director of Center for Civil and Building Service Engineering. And most of my research projects were funded by FHEA and in the UK. So for my presentation, firstly, I would like to give my research journey. I will introduce 2 main previous research projects. One is on the supermarket energy control system, and another one is child generation and its application in supermarket. And from those two projects, I realized the importance of waste heat recovery and power generation with advanced thermodynamic power cycles. And from there, I received a number of research fundings from industry, from FHEA, and in the UK. So here I will introduce some of the research outcomes from this funded research project on the power generation system with R245A, ORC, organic ranking cycles, and the power generation system with CO2 transcritical power cycles, we call it T-CO2, and the power generation system with CO2 transcritical or supercritical CO2 Brighton cycles. And finally, I will give some summary and also conclusions. And Deborah has already introduced, and I want to mention again about my degrees. And 25 years ago, I received respectively my BSc, MSc, and PhD degrees from Xi'an University for BSc and MSc, and Tsinghua University for my PhD. And these two universities are the top universities in China. And they were founded, I think, so one is founded in 1896, and one was founded in 1911. So both are slightly younger than the date founded in LSBU. LSBU even, they are younger brother, I think, compared to LSBU. And here I saw two pictures of Xi'an University, and one is the entrance gate of the main campus. I can see my laser point. And another one is the new campus of the university, and is the gate of the second campus. And the Xi'an University is located in the city of Xi'an. Xi'an is in history is a capital city of 13 dynasty, that one, yeah. And underneath these two pictures, you may see it from the television or from if you visit. This is the one hot point to visit if you visit China. So this is the terracotta army museum. And it was founded 2,000 years ago. And in I just give you a brief introduction. In 1974, I think a number of pigeons, they were trying to dig wells under the ground and found out this terracotta army. That one, yeah. So I think this is amazing things. This one you can see the individual is unique. You can't see two same terracotta soldier. So they see that expression totally different, unique, different. That one. And some people say this is the greatest discovery in the new century, the eighth discovery in the new century. So next time if you visit China, I recommend you to visit Xi'an and this terracotta army museum. That one, you can see the amazing discovery. And I also saw two pictures of Tsinghua University. One is the second gate of the Tsinghua University campus, and this is this one, yeah. And the theater hall of the Tsinghua University. It's quite a beautiful university. And underneath, you can see this is the Forbidden City, and the Great Wall. So this Great Wall and the terracotta army soldier were built at a similar period, 2,000 years ago. So one reason to build this terracotta army is because the emperor wants this army to protect his tomb. This is one reason for it. And this Great Wall, that one, the reason to build Great Wall is to protect the invasion from north. But nowadays, it's not useful to protect, because of the development of. Okay, so the topic of my PhD topic is on the experimental and modeling investigation of air conditioning system in buildings. That one, and from there I have developed my my research direction for my career development. So in the area of energy and modeling and also evaporating environmental investigation on built environment. So regarding to the research journey, that one, yeah. After I got my PhD, I came to the UK as a research fellow. I joined Brunel University as a research fellow. I remember my first project is a 3 years EPRC project on the energy control system in supermarket. And the motivation of this project is, we know in the supermarket, it consumes quite significant energy. So of the total energy consumption in the UK, it's about 3.5% is used in the supermarket. That one, yeah. Correspondingly, it consumes a lot. It can produce a lot of CO2 emissions. That one, yeah. So to save energy, to reduce the CO2 emission, we need to find out strategies. That one, yeah. So there is two main ways to obtain this strategy to reduce the energy consumption and reduce the CO2 emission. One is by modeling development, and one is by the environmental investigation. Considering the complexity of the supermarket energy control system, it's not possible to find out those strategies by purely experimental investigation. And the better ways is to develop a detailed and accurate modeling for the supermarket energy control system. So that's why I have developed the energy control system model for supermarket. And so in this slide, the model is an integration of 3 subsystem models. One is the building on the top, and one is HVAC system, so heating, ventilation, and air conditioning system. And the third subsystem is the refrigeration system. That one, yeah. So this is this system for the building model. So we need to have some essential inputs to develop the building model, including the zone classification inside the building, for example, the sales area and also the entrance door and so on. So where they have different temperature distributions, and also the fabric constructions. So this information we have obtained from our industrial partner. So we know the structural data. We know it from the operational supermarket, and also we need to know the infiltration, the gains, and also the time schedules and the controls. And also we need to know the interactions between the building and HVAC system and the refrigeration system, and also the local data. Depending on the location of the supermarket, we need to know the local weather data so that it can be input to the building model. And this is the HVAC system, that one. HVAC system is used to control the indoor space air parameters in terms of temperature and humidity by means of this air handling unit, that one. So in this air handling unit, you can see it consists of supply and return air fan and some heating coil and reheating coil. Because of the display cabinet, refrigerated display cabinet in the supermarket are located in the sales area inside the building, so it acts as the heat sink of the supermarket. So in the supermarket air conditioning system, the heating is more important. So most of the time, the cooling is not needed. So only heating is needed. So you can see here, there's no cooling coil in the air handling unit, only the heating coil, that one, yeah? So there's a second heating coil is from the superheat of the refrigeration system. So the refrigeration system can be integrated into the HVAC system. That one, yeah, this is the HVAC system. And this is the refrigeration system. We know in the supermarket we have chilled food, we have frozen food. The supermarket normally has 2 independent refrigeration systems. One is supply the cooling for the chilled food, one is used to supply the cooling for the frozen food. So for each refrigeration system, it consists of 4 main components: condenser, compressor, expansion, and the evaporator. The condenser is normally installed on the roof of the supermarket, and the compressors are installed in a special plant room. And the evaporator is installed just underneath each display fin. You can't see from the sales area to cool down the food stored in the cabinet. So that's why, because of the evaporator in the sales area, each cabinet can be used as a heat sink for the space in the sales area. So that's why the HVAC system will dominantly supply heating instead of cooling to control the indoor airspace parameters. So the integration of this three subsystem model will form the whole integrated supermarket system model. So on the top, the left top, you can see the energy breakdown of the supermarket energy control system. So refrigeration will consume about 30 to 50% of the overall energy consumption in the supermarket. And the lighting will be about 15 to 25%. And the HVAC system is about 20%, and the rest will be 20%. For the whole supermarket model, the most difficult part is the modeling of the refrigeration system because of the complexity of the refrigeration system. To model it, the most critical point is to predict the actual refrigeration load of each display cabinet so that we can calculate energy consumption of the refrigeration system at different operating conditions. So to do that, we use, so this pointer doesn't work, so I can't. So we use some ratios, RT and RL, to calculate the ratio of the actual refrigeration load and also the load at the rated condition. So to get this ratio, that one, we need to have the rated load for each display cabinet, which can be obtained from the manufacturer data. And the actual cooling load for a display cabinet can be obtained from the experiment or from the detailed modeling. So we choose to utilize our modeling to obtain the actual refrigeration load. Yeah, so the screen, you can't use the pointer for the screen. Yeah. So we choose to utilize to develop a detailed model for the display cabinet so that we can obtain the actual load for the display cabinet so that we can calculate the R and at different operating conditions. See here, the R is a function of the indoor space relative humidity, that one. Yeah, so once you, in the building model, if you have predicted the changed indoor air relative humidity, so you are able to calculate the R, and once you know the rated load from the manufacturer data, you are able to calculate out the actual load of the display cabinet. So what we do, we develop an innovative method to model this display cabinet. So normally this display cabinet model is using a separate model. Yeah, that one. Yeah, so what we use an integrated model, that one. Yeah, integrate two parts of the model to simulate the detailed display cabinet. One is the airflow dynamics of display cabinet and also the food inside the display cabinet. We're using the CFD model to model it. Another part of the integrated model is the evaporator model. So we're using in-house software to model it. So together, that one, to make the model more accurate because we don't assume any boundary condition for each model, that one. Yeah, because boundary condition has been solved out by this integrated model. And after that one, we develop this integrated model and operate this integrated model at the platform of transit, we call it transit, to run it, that one, yeah. So the output of the CFD model will be used as the input for the evaporator model, and the output of the evaporator model will be used as the input for the CFD model. So to make the model more practical and more accurate, so that we can obtain the function of the R for display cabinet cooling law. So here is the result from our modeling for the display cabinet. You see here, you can see the full temperature change with the room space relative humidity here. So what you can see from the top left diagram, so when the indoor space relative humidity increase, the food inside this cabinet, food temperature inside the cabinet is gradually increased. That means, so when you increase the indoor space relative humidity, the cabinet refrigeration load will increase, as shown in the bottom diagram here, that one. So when you increase indoor relative humidity, the refrigeration load will increase linearly, you see here. So from here, from this simulation result, we can obtain the functions of R listed in the last slide. And then we integrate it into our whole refrigeration system model of supermarket, so we can predict accurately for the performance of the refrigeration system. So once we have developed the whole supermarket model, we can run the model and to predict the performance data and also energy performance data for the whole year period. We can obtain the hourly performance data and the parameter for the whole year for the supermarket. And then we compare with the measurement so that we can validate our supermarket model. That one, yeah. So this result, you can see this is the simulation and the measurement result for the indoor air relative humidity during the whole year. This is hourly result. And the bottom one is the hourly variation of the power consumption of the compressor during the whole year period. You can see the modeling result match quite well with the measurement, that one, yeah. So once the model has been validated, so it can have quite significant applications. So one example of the model application is to evaluate and compare the refrigerant system performance when different refrigerants are used. That one, yeah. So we select two different refrigerants. One is R448, which is currently used refrigerant. One is the CO2. This is the future refrigerant for the supermarket. And we can compare the COP, this is the efficiency for the refrigeration system. You can see at different ambient air temperature. So what you can see from this simulation result, that one, so if the ambient temperature is lower, the CO2 refrigeration system performs better than the R448 system. So if the ambient temperature is higher, that means the CO2 system, the efficiency is slightly lower than that of R448 refrigeration system. So the research outcome from this project, we have published 8 journal papers, and also one software. We call it a Super Sim. That one is widely recognized in the world. That one for supermarket simulation. It has been cited quite a lot for this model. And the second research project, and it's what we did in Brunel, that one, yeah, and including both experimental and theoretical analysis. And I would like to mention that one, the experimental investigation is mostly carried out by Professor Isaka, that one, when he was working in Brunel as a research fellow, I think. So my main work for this project is on the modeling part, that one. So I use a lot of experimental results from ISA and to validate my model, that one, yeah. So for the experimental investigation for this tri-generation, we call it tri-generation. Some of you may not know about that. So tri-generation means this system will produce simultaneously electricity, heating, and cooling, that one, yeah. So we know in a supermarket, yeah, this energy are demanded simultaneously during the whole year. The supermarket needs cooling, heating, and electricity. So all the time, that one. Yeah, it's quite suitable for this tri-generation system to be applied in supermarket energy control system. So, and ESA has took the lead to develop this test rig, that one, yeah. For this test system, it consists of a number of main components. One is the 80 kilowatt micro turbine generator. That one, yeah, it's here. Yeah, but now is you can't point it out. I can yeah, this one, 80 kilowatt a micro turbine generator. That one, yeah, and you see here internal structure here in each micro turbine generator. It has a compressor, air compressor, and it has a turbine, gas turbine. That one, yeah, and also recuperator to enhance the efficiency of this micro turbine generator. And it has a combustor. That's a mixture of fuel and air and combustion. That one, and generate power. That one, yeah. And then it has integrated the hot water heater to produce heating. So originally, this micro turbine generator is used as a CHP unit, combined heating and power. That one, yeah. Since we want to use it in supermarket, we need to have a cooling purpose for this system. So what we do here, we add an absorption chiller here. That one, yeah. It's only 12 kilowatt cooling capacity. That one, yes, it's much less than the energy input from the exhaust gas of this CCiBSE system. So we're just using a bypass pipe to withdraw a little bit the heat from the exhaust gas. That one, yeah, so that it can produce refrigeration or cooling to the display cabinet. Yeah, the display cabinet is installed in a conditioned chamber, so we can test the performance of display cabinet. And the load of this cabinet is not large enough, that one, compared to the 12 kilowatt cooling capacity. So we're using excess dry blast unit to cover the excess cooling load. So this is the test rig for the chair generation system, that one, yeah. So we have a smaller cooling capacity, that one, yeah, because in the supermarket we need more cooling capacity, that one, yeah. So we do the experimental investigation, and in the meantime, so what this is my work. So I developed the model for the whole system, yeah, including the gas turbine, micro turbine system, and also the absorption chiller. So this is the integrated model of the micro turbine and the refrigeration system. So and then I run the modeling, that one, yeah, to predict the temperature of the air or flue gas, that one, at different fuel flow input, that one, yeah, because the fuel flow you can input with different values, that one, yeah. From this figure you can see here, that one, when you increase the fuel, yeah, natural gas, that one, fuel mass flow rate, you can see the temperature at the compressor outlet, that one, the turbine outlet, and also the CHP unit outlet, all increase, that one, increase slightly, that one, yeah. So the red color line, you can see that one, this is actually the exhaust from the CHP unit. The temperature is about 300 degrees C. So when the fuel mass flow rate reaches to 23 kilojoule per hour, that one, yeah. So this is quite a high grade temperature, that one. It can be used to generate power, can be used to heat, to energize absorption chiller system to produce cooling, that one, yeah. And this figure you can see here. So when you increase the fuel mass flow rate, the power generation from the CHP unit can increase up to 80 kilowatt, that one, 80 kilowatt, yeah, 80 kilowatt. And the right side, these two diagrams, that one, yeah, there is the power generation, that one, and also the change with the pressure ratio. The compression pressure, that one, there is the exhaust pressure is larger than the suction pressure. There's a pressure ratio. The pressure ratio can be changed, yeah, by changing the speed of the compressor motor, that one, yeah. So with the different pressure ratio, you can see the net power generation, that one, and also you can see the efficiency. Yeah, we define it as the FHEA is changed. So from this simulation, you can find out the optimal pressure ratio, which is around 3 for this particular micro turbine unit. So if you operate the pressure ratio at around 3, it can give you the maximum net power generation, that one, yeah, and also give you the highest the performance efficiency. Yeah, this is from the simulation result. And for the application of this charge generation in supermarket, the test rig is a smaller size, that one. It cannot be used directly to the application of a supermarket, that one. Yeah, to apply this charge generation system, we have investigated to an actual operational supermarket. So firstly, we need to know the typical energy demand of the supermarket in terms of electricity, refrigeration, and also the domestic hot water. So which are listed here, that one, yeah. So electricity for lighting and HVAC system, that one, the energy demand, electricity is 183 kilowatt, that one, yeah. And the refrigeration is 200, refrigeration for the medium temperature. And for chilled food, refrigeration is 260 kilowatt. And for low time frozen food, yeah, you see this refrigeration demand is 55 kilowatt. And also the domestic hot water is about 108 kilowatt. So we try to apply this charge generation system into this particular supermarket to meet this energy demand. So we did an initial design for this, that one, yeah. Since each microturbine generator can generate 80 kilowatts, so that is not enough for the electricity demand of the supermarket. So we select 3 microturbine generators, that one, yeah. Each one generated 80 kilowatt. So together is 240 kilowatt, 240 kilowatt, that one, yeah. So let's see how can this meet the energy demand of the supermarket. So we use 50 kilowatt electricity from this generator, that one, yeah, and we use our compression refrigeration system with a COP of 1 to produce 55 kilowatt temperature refrigeration, that one, yeah, see here. And we use another 70 kilowatt electricity to generate 176 kilowatt medium temperature refrigeration, that one, with the COP at 2.51. And the rest of the electricity is used for the lighting, HVAC system fan, that one, yeah, 115, that one. Yeah, since the electricity demand is 183, that one, 115 is not enough. So we need to have some electricity from the grid so that it can meet the electricity demand for the supermarket, that one, yeah. And in the meantime, we have some exhaust heat, that one here. Yeah, exhaust heat here from the turbine exhaust, that one, yeah. So the temperature we calculate out is about 300 degrees C, that one, yeah. So we designed 2 heat exchangers, that one, yeah, which are used to produce the domestic hot water, and another absorption chiller, because we have the exhaust heat, to produce the rest of the medium temperature cooling. So if you add this cooling together, add this domestic hot water and electricity together, they can exactly meet the energy demand of supermarket, that one, yeah. It seems this design is reasonable in terms of the energy balance, that one, a demand and energy supply, that one, yeah. But it is not necessarily reasonable, not necessarily the high efficient, that one, yeah. To get a high efficient and design, so what we need to utilize, not only using the analysis of energy, we need to utilize what we call ACG analysis, that one, yeah, ACG. Energy ACG, maybe some of you are not familiar with this if you are not in the area of energy. So ACG is I think, the scientist term to evaluate the energy capacity, we call it capacity, that one, yeah. So you have an amount of energy. That doesn't mean the energy can produce the useful work, that one, yeah, the useful work. So actually is used to evaluate the energy which can produce the useful work, that one, yeah, yeah. So different energy terms can have the same energy, that one, yeah, but the actually will be different, that one, yeah. For example, the heat and the electricity, that one, even they have the same amount of energy, but the actually will be different. Yeah, normally the electricity has has a higher XG, that one, yeah. Even for the same energy, if they have different temperatures, that one, the XG value will be different. The higher temperature, the higher the XG, that one, yeah. So to optimize the system design for the transgenerated system used in the supermarket, we need to utilize both energy and XG analysis so that we can identify the components where the best design can be developed. So we're using the energy and XG analysis method, that one, yeah. So the formula for this analysis are listed here, including the chemical reaction during the combustion process, that one, yeah. Depending on the airflow and also fuel flow, the ratio between them, the coefficient for this reaction equation can be different, that one, yeah. So normally for this trigeneration system, if you have more airflow, that means you have less exhaust gas, less flue gas temperature, that one, yeah. If you want to have a higher flue gas temperature, so you just reduce the airflow to the CHP or trigeneration system, that one, yeah. So it can be adjusted. And this is the formula. I don't want to go for it. I think it is quite particular, that one, yeah. So this is the XG efficiency is about 60%. The maximum is 100%. So you see you can have enough big room to improve the system design, that one, yeah. So so this efficiency, the maximum efficiency is the 100%. You see the difference. So by using this XG analysis, yeah, to summarize here, so for each equipment or heat exchanger, we carried out the XG destruction for each one, that one, yeah. So for this LT cooling and MT cooling and the hot water and also the MT cooling from the absorption, this is the XG destruction, that one, yeah. And correspondingly, we calculate out the actual efficiency for each equipment and the heat exchanger, that one, yeah. So we need to look at this, the largest actual destruction. So where is the useful work has been distracted. We need to find a way to produce more useful work, that one, yeah, that will work. So this is we call it the weak link we need to think about for the design, that one, yeah. For this are all for the refrigeration system, you can see, yeah. So you can think about that, refrigeration, for the condenser side, yes, a lot of energy will be exhausted to the ambient without using, that one, yeah, wasted, that one, yeah. That's why here you can see the XG destruction. So for the design, you can find a way to recover the wasted heat from the condenser exhaust and utilize it for the hot water production. In that way, so you can enhance the actual efficiency, that one, yeah. Now it's about 60%, so you can improve it for 7%. So by utilizing some wasted heat from the condenser of the refrigeration system, that one, yeah. And also for here, the hot water here, yeah. Although the destruction is slightly less than the refrigeration system, but if you compare these two, yeah, these two, both hot water, the reason is, you see here, back to here, see the temperature difference from the flue gas and the hot water. Hot water temperature is the same, 80 to 90. But the first one is about 300 and the 290. So the temperature difference is too large, that one, yeah. So make the larger XG destruction, that one, yeah. And the second one, you see, the temperature is quite close, 190 and 80-90. Yeah, this can give you a quite high efficient, that one, yeah. So this is actually you need to think about to redesign it. So instead of heat the hot water directly, maybe you think about another way, that one, yeah, to produce the electricity first. Because the temperature is quite high enough, it can be used to produce the electricity. Like the gas boiler, it is our gas boiler. Using the combustion gas to heat the hot water, actually the efficiency is quite low, that one, yeah. Compared to the CHP, that one, yeah, you're using the gas combustion to generate power first, and then in the meantime to produce the hot water. So that you can utilize efficiently for the energy supply, that one. Yeah, so our gas boiler at home is low efficiency. Although you see from energy point is quite high, but from actual point, that one, is quite low. Yeah, that one. Yeah, so that's why the CHP system is much better than the gas boiler. If you can produce a smaller domestic use CHP system, you can save a lot of energy. Maybe this is another direction to produce. Yeah. So here, this refrigeration system, because they have quite a low actual efficiency, if you only use the energy analysis, you can't find out that. So yeah, the energy is balanced. Yeah, that one. Yeah, but only the actual analysis you can find out that. That one. Yeah. So you need to find a way to do that, either by using waste heat recovery heat exchanger on the condenser exhaust side, or maybe using on the heat pump to upgrade the temperature. Yeah, and this one, yeah, because the temperature on the hot fluid side is about 300 degrees. If you use 300 degree the heat source to heat 8 degree hot water, you waste a lot of energy from the energy supply side. That one, yeah. So what we do when you think about to generate power from the 300 degree waste heat, yeah. So you have different ways to generate power by using the organic Rankine cycle or transcritical or supercritical CO2 cycle. Yeah, that is, from there, I think like I got some idea to develop from there, that one, yeah, from there to optimize the tri-generation system application in supermarket. We found out maybe we think about to have waste heat recovery and the power generation with some advanced thermodynamic power cycles, yeah, including the organic Rankine cycle, our CO2 transcritical and supercritical CO2 cycle. Yeah. So after that one, I obtained a number of fundings from industries, that one, and FHEA and Inaugural UK, that one. Yeah. So one is for the ORC. This is for the low-grade heat source power generation, and try this one, T-CO2. The later you can see this one, it can be used for a large range of heat source temperature, from low-grade temperature to high-grade temperature. That one, yeah. And this, and during the project for the T-CO2 power generation system, we found out some issues for that system. So mainly about the liquid CO2 pump, the leakage, and also in the current market, you can't find out a manufacturer to manufacture the CO2 liquid pump, that one, yeah. And then we think about utilize the compressor instead of liquid CO2 pump. So we brought another project, which is funded by the FHEA. Yeah. So we have time. Yeah. So for this project, that one, I think they have the similar background, that one, yeah, background. Yeah, we know in the UK, about 70% electricity consumed is generated from burning fossil fuels, so which consumes a lot of useful energy resources. That one also produce a lot of CO2 emissions. So in the meantime, we also have a lot of waste heat from industries. That one, we had different temperature grade. We have low grade. If the temperature is between 100 to 230, yeah, and 230 to 600 or about 650. So to recover this waste heat at different grade, we need to utilize that one, appropriate thermodynamic power cycles. That one, yeah, that's why we concentrate to analyze, yeah, the applicable thermodynamic power cycles, including R44A, R45FA, organic Rankine cycle, transcritical CO2 system, and supercritical CO2 system. So about this CHP unit, we utilize the exhaust gas as a heat source. That one, yeah, we develop a new test rig for the R2458 organic ranking cycle, that one, yeah. So here is the schematic diagram for this test rig system, that one, yeah. You see on the top is the system of the CIP unit and the exhaust. And the exhaust from CIP unit is used to heat what we call the heat transfer medium, thermal oil, that one, yeah. No directly so heat the evaporator of the ORC system, that one, yeah. So thermal oil is circulated, yeah, that one, to the ORC system to heat the ORC system, that one. And the organic ranking working fluid temperature and the pressure will increase, that one, yeah. When heated by the thermal oil and then expanded in the ORC turbine to generate power, that one. Yeah, after that, we use a recuperator to enhance heat transfer, and also we have the condenser, that one, to release the heat to the ambient, to change the working fluid from the vapor to the liquid, and pumped back to the recuperator and the evaporator, and the cycle will be repeated. And underneath here is the TS diagram of the ORC cycle, yeah, and also the variation of the heat source and the heat sink, that one, yeah. So you can see here, this is the dome for the working fluid. So this cycle is under the critical point, so we call it subcritical power cycle, that one, yeah. And here you can see some pictures about test rig. So underneath is the CHP unit, 80 kilowatt micro turbine generator, and above that is the component. You can't see that clearly, that one, yeah, because some of components are insulated, so you can't see it clearly, that one, yeah. So you have oil rig, you have ORC rig, and also the condenser here, here. And I have, I don't know if I can run it or not. This is a short video to see the whole test rig. So I don't think I can run it here. Oh. Yeah. This is, you can see the top of the rig. It's quite big, just I think it's the whole roof of the CHP unit, that one, yeah. And right side is the operation of the integration of the screw turbine, screw expander, that one, of ORC system, and also the motor over here, that one, yeah. So I stop here, so this one, yeah. And this is the motor, this is the belt connection here, yeah. So I just quickly run it, you can see the operation here. You see the system. Yeah. This is my research RA, is RA from China. He's now a professor in university in China. Yeah, and this project, a number of PhD students have involved in this project, and one research fellow who are involved in this project. Okay. Oh, this can run as well. Yeah. Yeah, just to give you some test results, not all the results. That one. Yeah, the one result is the system pressure at different heat source temperature. That one. Yeah, this one here, and also the turbine power generation, turbine power generation, and the pump power consumption with the different heat source temperature. So what you can see here, when you increase heat source temperature, that one, yeah, the pressure on the high pressure side and on the low pressure side are all increased. So there are some difference for each side. That one, this is because of the pressure drop, yeah, for each component and along the pipe. So you can see the dotted line is the pressure ratio of the system. When you increase the heat source temperature, the pressure ratio will increase. And the power generation from the turbine will increase as well, and also the heating capacity and the cooling capacity of the condenser will increase as well with the high heat source temperature. And from here, what you can find out, if you want to control the pressure of the system, so one way is to increase heat source temperature. This is what we found out, this one, yeah. And another is the pump speed, that one, yeah, for the organic ranking cycle. So you can vary you can modulate the pump speed. So the pump speed can affect the pressure of the system as well. You can see when you increase the pump speed, the high side organic ranking cycle pressure will increase. And in the meantime, the low process side, the pressure will increase as well. And the pressure increase in the low pressure side is larger than the pressure increase on the high pressure side. That's why the pressure ratio will decrease with the high, will increase of the pump speed. That's why, yeah. So from here, you can also create a function so that you can control the ORC pressure by modulating the pump speed. Yeah. So this tri-generation system, that one, so you see the working fluid is different. Previously we are using the R245A, that one. Yeah. Now for this tri-generation CO2 system, we are using CO2 as a working fluid. So here, this is the system schematic diagram for the system. It's similar to the organic ranking cycle, that one. Only the working fluid is different. But the cycle for this tri-generation, so the reason we call it tri-generation, that one, yeah, because this system has two levels of pressures, the lower level and higher level. So the lower level is under the critical pressure, and the higher level is above the critical pressure. So we call it transcritical CO2 power cycle, CO2 cycle here. And we just install this tri-generation CO2 power cycle beside the organic ranking cycle, since we are using the same heat source from the CHP unit, that one, yeah. So this is OU rig, which supplied the heat source for both systems, that one, yeah. So the OU will hold, so that we can run these two systems separately, that one, yeah. So one heat source can supply the heat for both systems. And here, just give you some picture about this system components, that one, yeah. This is the component of the heat exchanger, mostly the plate heat exchanger, and also we are using receiver, air-cooled condenser, and the turbine. That one, yeah. So I think what we did, we were nearly the first who developed this test rig for tri-generation transcritical CO2 cycle, and this turbine actually not many, only I think in the world only one manufacturer from France, they manufacture this turbine, CO2 turbine, and the CO2 pump. This is not particularly for the transcritical CO2 system, so we found a lot of leakage because this is not the first time to be used in this transcritical CO2 system. So we found a lot of issues for that. That one, yeah. Turbine efficiency is not that high because this is the first manufactured CO2 turbine, and we tested it. That one, yeah. And since now maybe they have quite a better high quality turbine, but at that time the quality is not that good in terms of the electricity efficiency. It's quite low, that one. Yeah, even you have quite a high isentropic efficiency, the electric efficiency is quite low. In the end, the power generation from the turbine is quite low, that one. Yeah, because a lot of things need to be improved, that one. Yeah, but they are quite expensive as well, that one. Yeah, even though this is the first manufacturer in the world, but they are quite expensive. Yeah, so this result are similar to the ORC one. I don't want to go, because of the time, that one, I don't want to go to data details, that one, yeah. So main things, yeah, that one, so you still can use the heat source side, heat input to control the pressure in the transcritical CO2 cycle. Yeah, so from what we found from the experimental investigation, it's difficult to compare and evaluate these two systems, one ORC and one CO2 system, that one, yeah. And the best way is to develop a reasonable model, that one, so that you can have a larger operating range, that one, yeah. And you can find out the applicable operating condition for each system, and also you can optimize for each system, that one, yeah. So this is why we develop a model. This is quite a simple model, that one, yeah, but it can have quite a good conclusions, that one, yeah. So this is R245A ORC system, one is a CO2 transcritical system. So if you look at the thermodynamic property for these two working fluids, that one, in terms of critical temperature, critical pressure, and also maximum temperature is quite important, that one. You see, if the working fluid has a higher temperature, more than 440, so that working fluid will be broken down, that one. Yeah, that one you can't use anymore. So that's why this R245A ORC system can only be used in the low-grade waste heat applications, cannot be used for the high temperature waste heat recovery. That one, yeah. But so CO2 is different. That one you can see here. CO2 has a quite low critical temperature, quite high critical pressure, but it's quite high maximum temperature, 2000 K. That one. Yeah, that means no matter how high the waste heat is, you can utilize CO2 as a working fluid for the power generation. Yeah, no limitation. But the ORC, there is a limitation for that. It can only be used for the ORC low-grade waste heat recovery. And the GWP, that one, R245A, need to be replaced in the future because of the higher global warming potential working fluid. So what we do, that one, to evaluate these two systems, that one, we need to find out the applicable operating conditions for each working fluid, each power generation system, that one, yeah. So because of the high, see here, the critical pressure and also the highest maximum temperature for the ORC system, that one, so the maximum heat source temperature, that one, need to be kept within about 400 degrees C, that one, yeah, 100 degrees C, yeah. So you assume the heat source temperature is the same as the turbine inlet temperature. This is just the assumption, that one, yeah. Actually, there are some temperature difference, that one, yeah, here. And the pressure for the ORC system can be controlled to be different values, that one, yeah. So, but you need to make sure that the highest, the ORC pressure, be a little bit lower than the critical pressure. So that's why we choose about 30 bar for the ORC system, that one, yeah. Because the critical pressure is about 35, 36 bar, that one, yeah. So they have quite a good heat transfer on the evaporator side, that one, yeah. And for the low side pressure, that one, is depending on the heat sink temperature. So we assume the heat sink temperature is about 20 degrees C. So we can determine the low side pressure, PC, that one, yeah, for both cycle, yeah. And this is for the CO2 transcritical cycle. Yeah, there's no limitation for the high side pressure. That one, yeah, see, because it is transcritical, it's above the critical pressure. That one, it can be higher, 120 bar, 140 bar. That one, and the temperature, no limitation. Yeah, whatever. That one, yeah, as long as it's less than 2000 K. That one, yeah. So no limit for the transcritical CO2. Yeah, so you can specify the operating conditions for both systems, that one, yeah. And then you do, similarly to the trigeneration, do the energy and the XG analysis, that one, so that you can optimize the system, that one, yeah. So we do some calculation for both systems, that one, yeah. So this is the pressure from 10 bar to 30 bar. This is the range. 5 bar to 30 bar. This is range for the ORC system. Yeah, it's better not above or below that one. Yeah, and we calculate thermal efficiency and also actual efficiency for each operating condition. That one. Yeah. So what we found here, for this low grade waste heat, 90 degrees C, thermal efficiency is lower. Yeah, the higher the heat source temperature, the higher the thermal efficiency, but not necessarily the actual efficiency is higher. You can see the low-grade waste heat input, you have higher actual efficiency. That means the energy utilization is higher, it's maximized. So here we just give you some optimal design. Then for this system, so we think that the lower, the better. That one, yeah, because they have high efficiency. And the pressure, yeah, the higher the better. That one, yeah. So 90 degrees C, 10 bar is the optimal design for this organic ranking cycle. And for this, that one, yeah. So the heat source time, the higher, the thermal efficiency, the higher. And the actual efficiency is quite close, that one, yeah. So you can assume they are more or less the same, that one, yeah. So the optimal design is the heat source temperature is higher than 380, and the pressure is even more than that, but the higher you need to have special design for the heat changer. Yeah, so we assume this is 140 bar, 40 bar, yeah. So this is just, this is from the optimal design point of view, that one, how to optimize the energy system, that one. Yeah, we utilize both the energy and energy analysis. We think this is reasonable and the better way for the analysis and the optimization of energy system. So from what we have done in the previous projects on the ORC and the transcritical CO2, what we found, we have found some issues, that one, yeah. So the thermal and active efficiency are really low for R245A ORC due to the limited heat source temperature, because due to the limited maximum temperature of the working fluid. And the R245A has a high global warming potential, so in the long future, so we can't use it as a working fluid. And the thermal and active efficiency are also little low due to the high temperature difference between the limited heat transfer, the heat transfer medium, and also for the CO2 transcritical CO2 system, which has a limited maximum CO2 temperature. That one, yeah. So theoretically, we can have the high, but practically, so because we are using the thermal oil as a heat transfer medium, the thermal oil has a maximum temperature to be used, about 350 degrees C. So you can't have the temperature higher than that. So it's difficult to achieve practically the high temperature above 300 degrees for CO2 system. That one, yeah. And also what we found, that one, the high power consumption of the CO2 liquid pump, some issue for that, and also the low efficiency of the CO2 turbine, that one, yeah, and also the leakage, the CO2 pump. So that is not practical. So we need to find an alternative way to pressure up the CO2 from low pressure to the high pressure. Instead of using the liquid pump, maybe we can think about using compressor. Because compressor is easier to find out from the market, that one, yeah, but you need to change the design for the power generation system if you are using the same working fluid of CO2. So that's why we obtained another funding for the CO2 power generation system. But this time, that one, we are using different thermodynamic power cycles instead of using the transcritical CO2 power cycle. So we were using the transcritical CO2 Brighton cycle, so that the working fluid compression is using the compressor instead of using the liquid pump. Yeah. So here is the system layout. That one. Yeah. Yeah. We are using this time. We didn't use the CHP exhaust gas. We are using the flue gas from a biomass boiler. So this the biomass was manufactured from our industrial partner, biomass company, and the flue gas from the biomass boiler, the temperature is about 800 degrees C. That one, yes, high enough. That one, yeah. And this flue gas is used to heat the CO2 gas heater directly instead of using the heat transfer medium, so that the CO2 temperature can be heated up about 500 degrees C, 100 degrees C. Yeah. And here, so instead of using the air-cooled condenser for the ORC and the transcritical CO2 system, we're using the water-cooled condenser. Yeah, that's one. Yeah, we have a cooling water loop here. That's one. Yeah. So the right side is the system cycle. You can see here. That one. Yeah. The low pressure is below the critical pressure. The high pressure is above the critical pressure. It's still transcritical, but we call it transcritical Brighton cycle since there is no liquid in the cycle. That one, yeah, we call it transcritical Brighton cycle. And we're using the conventional compressor to pressure up the CO2. That one, yeah, is easier to find out from the market. And also this is the system cycle here, and the temperature CO2 temperature can be as high as 500. And here is some equipment. That one, yeah, equipment, the gas biomass boiler, and this is the main test rig, and that one is the water cooler. Yeah. Yeah, it's nearly there. And we did some simulation for that to investigate the effect of the heat source temperature at one, the heat source temperature and also the turbine inlet pressure on the power generation and also the system efficiency here. So you see here, this is quite interesting result here, that one. Yeah, for the turbine inlet pressure, we can find out an optimal value for it so that the efficiency at each heat source temperature, you can find out the maximum efficiency. So you can optimize the turbine inlet pressure for this, we call it the transcritical CO2 Brayton cycle. Yeah. Okay, yeah. And because of time, I just give some summaries about my presentation. That one, yeah. I know something are quite special. That one, if you are not working in this area, maybe it's difficult to understand. And just give you some summaries from my presentation. And the ORC and the CO2 power cycles are applicable for waste heat recovery and power generations at different heat source temperatures. That one, yeah. And the ORCs are more applicable to low-grade waste heat source, where CO2 power cycles, such as transcritical CO2 ranking and the Brayton cycle, can be applied to heat source with different temperature grades. That one, yeah, not limited to the low pressure, can be higher as well. And the applicable transcritical CO2 ranking cycle are limited by the applicability of transcritical CO2, CO2 liquid pump, CI2 or CO2 liquid pump. And the combined thermal or energy and the XG analysis, these are quite powerful and are significant for system performance and the design optimization. That one, yeah. And I also would like to the contribution from my PhD students and also research fellow for those previous projects. That one, and thank you for your attention for this, and thank you very much. Yeah.
Thank you, Yunting, for a very inspiring presentation. A lot of mathematics and modeling in there. I've been given the task of saying a few words on behalf of the Dean and the student of the school and the university. And first of all, thank you all for your attendance. One of the elements, and from what Yunting has presented, is that some of these pictures bring memories of Yunting and I working together back in early 2000 or something, 2001. I was actually asked to go and ask Yunting about the modeling of the actual tri-generation system which I designed at Brunel. But when I got there and I found, I'm going to ask this guy how to do the modeling, I found there was a queue in front of me. So there was other people waiting before me to ask Yunting. And you can see Yunting has got a computer, a desktop, and a laptop, and the model working at the same time. And he's multitasking between the two, as well as helping other colleagues, researchers, which was lovely. So when I got to him, he not only helped me, but he gave me a homework to go and do at home. And then he said, come back tomorrow, show me what you've done. And that was really good, because he was checking whether I practice what he told me. So Yunting, not only he has come in from one of the top universities in China, he's come from a city which is renowned for its heritage. Xi'an is a city with as Yunting has showed, the famous terracotta warriors, and the universities that he's come from are some of the top universities, 17th in the world ranking and 18th in the QS rankings. So that's some of the top universities in China. One of also the first #1 in Asia. But you may wonder why he's chosen LSBU. Actually, Yunting and LSBU goes a long time, because while he was at Brunel, he was also supporting us, and in the field of building services engineering, we are a small community. We work together. Everybody knows each other. And Yunting used to come to LSBU and help us. And then he became our external examiner. for the subject area of building services engineering. And the opportunity came for some strategic appointments in the school, and he was one of the successful candidates in that appointment, and we are pleased that he has been one of the successful candidates. Because one of the elements that Yunting has developed is actually the churning of ideas. I was the one working on the actual generation, but he's already written the next proposal before me, because he's had the ability to visualize and look from outside the box at the next idea, the CO2 system, the organic ranking cycle, and so on. And I used to wonder, how does Yunting works this fast, all the time churning these ideas? Until one day I went and saw him looking at the models and just going back and forward, and then going saying, okay, like he was walking here, and I said, why are you walking? And he says, you know, I used to be a high jump champion in the university, and he used to think outside the box all the time. So there is Yunting all the time thinking outside the box, and he is always churning these ideas. So his contribution to LSBU has been, he actually joined us. We were successful in March, but in April, before joining LSBU, he's got 2 months, he said, I've got this proposal which I need to submit before joining LSBU. How can I do that? And he submitted the proposal, we discussed the proposal, he submitted it, and by the time he joined LSBU, it actually won. So this is absolutely brilliant. Yunting had the ability to generate ideas, to develop ideas, but also to win proposals. But not only win proposals, his contribution has been immense to his colleagues. Ever since Yunting took over the director of the CCiBSE, he has been using the funds that have been allocated to the center to help and initiate new projects, ideas, to support colleagues to develop projects and ideas, and also he's been mentoring colleagues and students. I'm very pleased to hear that Yunting is actually engaging students in the lab, and the graduate and MSc students, modeling using CFD modeling as well as doing practical work. So he's a research-informed teaching champion within the school, and I'm proud, we are all proud of this. In the long term as well, we expect, you know, he's got lots of ideas, and he's been working with colleagues, saying he's already identified about 5 or 6 colleagues to join him on projects and writing new projects. But so the future is we expect lots of projects from Yunting, and I think we are very proud that we have Yunting amongst us, working to develop knowledge, research, and innovation, but also to develop research-informed teaching that will find application in the sector. I'm very proud to be working with you, Yunting, and with seeing your students are here supporting you. It is really a great pleasure to listen to you, to see some of the work and the extent of innovation and knowledge contribution you've done. Thank you very, very much. Thank you. It gives me a great pleasure on behalf of the university to hand this over to you, Yunting.
It's my pleasure to work here at SBU, and hopefully I think I work together to achieve more in the near future.
Thank you. We will be having some refreshment next door, and where the discussion can continue with Yunting. Thank you all for attending today, and we look forward to seeing you at the next inaugural lecture, which will be next week. Thank you.